All right. So uh, we already talked about calculating the electric stress in a single core cables. So I just finish up to here, and then we wanna finalize, find the maximum potential gradient. So this slide explains the condition for maximum potential gradient in a cable insulation system. From the previous equations, we know that the potential gradient G is equal to V divided by X uh, log D over D, capital D over D, varies inversely with radial distance x from the center of the conductor. So this means that as the distance x decreases, the value of potential gradient increases. Therefore, the maximum potential gradient occurs when x is at its minimum value, so which is at the surface of the conductor. Since the conductor diameter is represented by d, uh, the minimum radial distance is equal to x equal to d over t 2. And by substituting this value into the equation, we can obtain the maximum potential gradient. So this shows that the electric stress is greatest at the conductor surface and decreases gradually toward the sheath. So this result is very important in high voltage cable design because insulation failure is most likely to begin where the electric stress is highest. So you must therefore ensure that the insulation surrounding the conductor is strong enough to withstand this maximum electric field and maintain safe and reliable cable operation. Okay, this slide explains the condition for minimum potential gradient in a cable insulation system. Since the potential gradient is given by the equation G is equal to this value, it varies inversely with the distance x from the center of the conductor. Okay, this means that as the distance is x increases, the value of the potential gradient decreases. So therefore, the minimum potential gradient occurs when x reaches its maximum value, which is at the inner surface of the sheath. So since the sheath diameter is represented by d, the maximum radial distance is equal to x is equal to d over 2. So by substituting this value into the equation, we can obtain the minimum potential gradient. This indicates that the electric stress is lowest near the sheath surface compared to the conductor surface. The difference between maximum and minimum potential gradient is important because it shows that the electric field is not uniformly distributed across the insulation. Understanding this behavior helps you improve insulation design, optimize cable dimensions, and ensure long-term reliability and safety in high voltage underground cable systems. So this slide, I think this slide is one of your major two questions. So this slide explains the variation of the electric stress within the insulation of a cable as shown in figure 11.14. The graph shows that the electric stress is not uniform throughout the insulation thickness. It reaches its maximum value at the surface of the conductor where the radial distance is a minimum and gradually decreases as we move outward toward the sheath. So this happens because the potential gradient varies inversely with the distance from the center of the conductor. As a result, the electric field is strongest near the conductor and weakest near the sheath. So this uneven distribution of stress is a critical factor in cable design because the insulation closest to the conductor is subjected to the highest electrical stress and is therefore more vulnerable to breakdown. So you must pay special attention to the maximum stress when selecting insulation materials and determining insulation thickness. So proper management of the electric stress helps improve the performance, safety, and service life of high voltage power cables. Okay, this slide highlights the practical importance of maximum dielectric stress in cable insulation design. For example, if a cable operates at voltage that produces a maximum stress of 5 kilovolt per millimeter at the conductor surface, then the insulation material selected must have a dielectric strength of at least 5 kilovolt per millimeter. The electric strength refers to the maximum electric field that an insulating material can withstand without failure. If the insulation cannot tolerate this stress level, electrical breakdown will occur, leading to insulation failure, short circuit, and possible damage to the entire cable systems. Let me add a new student. All right. Since the highest stress always occurs near the conductor surface. This region requires the greatest attention during design, and you must carefully choose insulation materials with sufficient electric strength and provide an adequate safety margin to ensure reliable operation. So this principle is essential in high voltage cable engineering because the long-term performance and safety of the cable depend directly on the ability of the insulation to resist maximum electric stress. All right, this slide presents an example of electric stress distribution in a single core cable operating at 33 kilovolt. The cable has a conductor diameter of 1 centimeter and an internal sheath diameter of 4 centimeter. The analysis focuses on determining the maximum and minimum electric stress within the insulation. The maximum stress occurs at the surface of the conductor and is calculated using the logarithmic relationship between the sheath and conductor diameters, resulting in a value of approximately 47.61 kilovolt per centimeter RMS value. In contrast, the minimum stress appears at the inner surface of the sheath, where the electric field is weakest and is found to be about 11.9 kilovolt per centimeter RMS, and this value can also be derived proportionally from the maximum stress using the ratio of conductor to sheath diameter. So in overall, this example highlights how electric stress is non-uniformly distributed across cable insulation, being highest near the conductor and decreasing toward the inner sheath, which is critical consideration in cable design and insulation reliability. Okay, this slide explains how to determine both the insulation thickness and the operating voltage of a single core cable based on given electric stress limits. The maximum and minimum dielectric stress are provided as 40 kilovolt per centimeter and 10 kilovolt per centimeter RMS respectively, with a conductor diameter of 2 centimeter. Using the relationship between maximum and minimum stress, the sheath diameter is calculated to be 8 centimeter. From this, the insulation thickness is obtained as 3 centimeters, showing how the geometry of the cable directly depends on the allowable stress levels. The second part of the example focuses on finding the operating voltage by applying the standard equation for maximum electric stress in a cable and substituting the known values. The operating voltage is determined to be approximately 55.45 kilovolt RMS. Overall, this example demonstrate the practical application of electric stress relationships in cable design, linking physical dimensions with electrical performance to ensure safe and efficient operation. Okay, this slide present a comprehensive example of analyzing a single core cable operating on an 11 kV 50 Hz system focusing on electric stress and key electrical parameters. The conductor has a cross-sectional area of 0.645 centimeter power 2, from which the conductor diameter is calculated as approximately 0.906 centimeter, while the internal sheath diameter is given as 2.18 centimeter. Using these dimensions, the maximum electrostatic stress is determined at the conductor surface, yielding a value of about 27.65 kilovolt per centimeter RMS, which represent the highest electric field intensity within the insulation. Conversely, the minimum electrostatic stress occurs at the sheath and is calculated as approximately 11.5 kilovolt per centimeter RMS, indicating the non-uniform distribution of the electric field across the dielectric. Let me add new student. Okay, this example highlights how cable geometry and material properties such as permittivity influence stress level, which are critical for insulation design, reliability, and preventing dielectric breakdown in power cable systems. So this slide explains how to calculate the capacitance of a cable and its corresponding charging current. So the capacitance C depends on the relative permittivity of the insulation, epsilon R, the cable length L, and the ratio of conductor spacing to conductor diameter D over D. By substituting the given values, epsilon R is equal to 3.5 and L is equal to 1 kilometer, the capacitance is calculated using the logarithmic expression, resulting in approximately 0.22 microfarad. So this highlights how insulation properties and geometric configuration influence the cable's ability to store electric charge. The second part of the slide also focus on the charging current, which rises due to the cable capacitance when an AC voltage is applied. So IC is equal to V over XC, and by using of this equation, we can find this current, and this demonstrates that even in the absence of the load, underground or long cables draw a capacitive current. So this is very small, but it's possible, which is an important consideration in power system design, especially for voltage regulation and reactive power management. Okay, this slide introduces the concept of the most economical conductor size in a cable. As discussed earlier, the maximum dielectric stress in a cable occurs at the surface of the conductor because the electric field is strongest at the point where the radial distance is minimum. For safe and reliable operation, the dielectric strength of the insulation must always be greater than this maximum stress. If the insulation strength is lower than the electric stress at the conductor surface, insulation breakdown becomes unavoidable. So therefore, selecting the correct conductor size is not only an electrical consideration, but also an economic one. A very small conductor increases the electric stress and require stronger and more expensive insulation. So while an excessively large conductor increases material cost unnecessarily. So the most economical conductor size is the one that provides a balance between conductor cost and insulation cost while maintaining safe operating conditions. So this principle is very important in high voltage cables design because it ensures both technical reliability and cost effective system performance. So this slide explains the next step in determining the most economical conductor size in a cable by rewriting the expression for maximum dielectric stress. Since the maximum stress occurs at the surface of the conductor, its value depends on the operating voltage, conductor diameter, and sheath diameter. By expressing the maximum stress in terms of these parameters, you can analyze how changes in conductor size affect the electrical stress in the insulation. In practical cable design, the working voltage V and the internal sheath diameter D are usually fixed because they are determined by system requirements and design limitations. This means that the only variable that can be adjusted is the conductor diameter D. Therefore, finding the most economical conductor size becomes a problem of selecting the optimum value of D uh, that minimize the maximum stress while also keeping material cost reasonable. So this approach helps achieve both safe insulation performance and economic efficiency in high voltage cable systems. Also, this slide is one of your multi-choice question and in major two. So, okay, this slide explains why the conductor diameter D becomes the key factor in determining the most economical cable design. Since the working voltage V and the internal sheath diameter D are fixed due to the design and operational requirements, the conductor diameter is the only remaining variables in the expression for maximum dielectric stress, G maximum. For safe cable operation, the goal is to reduce the maximum stress at the conductor surface because this is the point where insulation failure is most likely to occur. Therefore, for given values of V and D, the most economical conductor diameter is the one that makes G maximum as small as possible. In other words, the optimum conductor size is obtained when the maximum dielectric stress reaches its minimum value. This condition allows the use of insulation with suitable dielectric strengths without unnecessary increase in conductor material cost. As a result, both electrical safety and economic efficiency are achieved in the cable design. So this slide explains the condition for minimizing the maximum electric stress G max in a cable. The key idea is that the electric stress becomes minimum when the expression D ln D over D is can be maximized. So where D is the conductor diameter and the capital D is the overall diameter, including the insulation. So to find this optimal condition, the expression is differentiated with respect to D and set equal to 0. So by expanding and simplifying the derivative, we can obtain the conditions. So ln d over d minus 1 is equal to 1, and finally d over d is equal to Neper value. So Neper value is equal to 2.718. So this result is very important in cable design. It shows that for minimum dielectric stress, the ratio of the sheath diameter to the conductor diameter must be equal to Euler number, or E. In practical terms, this provides an optimal insulation thickness that ensures the electric field is distributed more uniformly, reducing the risk of insulation breakdown and improving the reliability of the cable. Okay, the most economical conductor diameter is obtained by optimizing the relationship between conductor size and the associated cost and performance constraints. Under this condition, the maximum value of G maximum occurs when the design is optimized for minimum cost while maintaining acceptable electrical performance. So mathematically, this optimum point can be determined by substituting log d over d is equal to 1, so into this expression, so which simplifies the analysis and yields the condition for the most efficient conductor sizing. And this result provides a practical guideline for selecting conductor dimensions that balance material usage and electrical efficiency. Okay, for low and medium voltage cables, the conductor diameter obtained from the expression d is equal to 2v over g max is often found to be too small when considered from the standpoint of uh, permissible current density. So in practical applications, such a reduced diameter may lead to excessive heating and inefficient current carrying capability. Therefore, instead of relying solely on the electrostatic optimization criterion, the conductor size is typically selected based on safe current density limits. So this ensures that the cable operates within thermal safety margins while maintaining reliable and efficient current condition under normal operating conditions. Okay. So for high voltage cables, the design approach based on this theory results in comparatively a large value of conductor diameter, which is significantly higher than what would normally require from the standpoint of current carrying capacity alone. So in such cases, the increase in conductor diameter is actually beneficial as it helps in achieving a more uniform electric field distribution and reduces electrical stress within the insulation. So therefore, it is advantageous and practically justified to adopt this larger conductor diameter since it improves the overall dielectric performance of the cable while remaining acceptable from the current carrying perspectives. Okay, there are several practical methods to achieve the required conductor design without using excessive amounts of copper. One approach is to use aluminum instead of copper, since for the same current rating, aluminum requires a larger conductor diameter, making it a cost-effective alternative. Another method is to use copper wires stranded around a central core of hemp, which helps reduce material usage while maintaining a structural flexibility. A further option is to replace the HEM core with a central lead tube, which can provide improve mechanical strength and insulation characteristics. These techniques allow designers to optimize cable construction while balancing performance, material costs, and mechanical requirements. Okay, this example demonstrates how to determine the most economical conductor diameter for a single core cable operating in a 50 kilovolt single phase system subject to maximum allowable dielectric stress. So first, the peak value of the cable voltage is calculated from the RMS value using the V peak is equal to 50 times square 2. So the maximum permissible electric stress in the insulation is given as G maximum, 40 kilovolt per centimeter, which is assumed to be the peak value. To obtain the most economical design, we use the standard relationship between conductor diameter, operating voltage, and maximum stress, this value. So by substituting the given value, the conductor diameter can be calculated as 3.53 centimeter. So this result indicates the optimal conductor size that ensures the electric stress does not exceed the safe limit value while also achieving an economical insulation design. So it reflects the practical application of electric field theory in cable engineering, where both performance and cost consideration must be considered and should be we have to find a trade-off between them. Okay, this is another example. This slide presents the calculation of the most economical size for single core cable operating in a 132 kilovolt three-phase power systems when the allowable dielectric stress is limited to 60 kilovolt per centimeter. First, the line voltage is converted into phase voltage by dividing 132 kilovolt by the square root of 3, giving 76.21 kilovolt. Then the maximum or peak phase voltage is determined by multiplying the phase voltage by the square root of 2, resulting in 107.78 kilovolt. So using the economic design formula, the optimum conductor diameter is calculated as twice the peak voltage divided by the maximum permissible stress. We already discussed about that, which gives the 3.6 centimeter. So after obtaining the conductor diameter, the internal diameter of the sheath can be found by multiplying the conductor diameter by 2.718. This is a Euler value. So I already told you. So this example also demonstrates how electrical stress limitations directly influence cable dimensions and help you achieve a safe and cost-effective insulation design. Okay, what is cable grading? Cable grading refers to the process of achieving a more uniform electrostatic stress distribution within the dielectric material of the cable. The primary objective of grading is to reduce the maximum stress and improve the overall reliability and efficiency of the insulation system. So this is particularly important in high voltage cables where non-uniform stress can lead to insulation failure. So there are two main methods used for grading of cables, capacitance grading and intersheath grading. Capacitance grading involves the use of different dielectric materials with varying permittitives to control the stress distribution. Inter-sheath grading, on the other hand, uses additional conductive layers, inter-sheaths placed within the insulation to redistribute the electric field more uniformly. Okay, capacitance grading is a method used to achieve a more uniform distribution of dielectric stress within the cable. So this is accomplished by using multiple layers of different dielectric materials, each having a different permittivity, so that the electric stress is more evenly distributed across the insulation. In this technique, the originally homogeneous dielectric is replaced by a composite dielectric system. By carefully selecting and arranging these dielectric layers, the maximum stress within the insulation can be reduced, thereby improving the overall performance and reliability of high voltage cables. Okay, the composite dielectric used in capacitance grading consists of several concentric layers of different dielectric materials, each having different relative permittivity. These layers are arranged in such a way that the relative permittivity epsilon r of each layer is inversely proportional to its distance from the center of the cable. In other words, materials with higher permittivity are placed closer to the conductor, while those with lower permittivity are positioned farther away. So this arrangement helps in achieving a more uniform distribution of electric stress across the insulation, thereby improving the dielectric performance and reliability of the cables. So this slide explains how the electric stress inside the cable insulation can be made uniform by using dielectric materials with varying permittivity. So the electric field intensity is given by the equation where it is inversely proportional to the product of the radial distance x and the relative permittivity epsilon r. To achieve constant electric stress throughout the insulation layer, the relative permittivity is assumed to vary with distance from the conductor radius r to the sheath radius capital R, so such that it is inversely proportional to x, or expressed as epsilon r is equal to c over x, where c is a constant. So substituting the relationship into the electric field equation removes the dependence on x, resulting in a constant electric field. So this means the electric stress remains the same at every point between the conductor and the sheaths. Such a design is highly beneficial in cable engineering because it prevents excessive stress concentration near the conductor surface and improves the overall insulation performance and reliability of the cable system. Okay, this slide presents an example of electric stress analysis in 100 kilovolt single core lead. So sheeted cable with graded insulation. The conductor has a radius of 1 centimeter, while the internal sheath radius is 4 centimeter. The insulation is divided into two dielectric regions. The first radial layer of 1 centimeter thickness has a higher relative permeability of 5, and the remaining insulations has relative permeability of 3. The objective is to determine the maximum and minimum electric stress in each dielectric layer. Because the dielectric constants are different, the electric field distribution will not be uniform, and the stress changes at the boundary between the two materials and the inner layer with higher permittivity helps reduce the maximum stress near the conductor surface where electric stress is usually highest. After calculating the stress values, the results are compared with those of a cable having the same physical dimensions but homogeneous insulation throughout. This comparison demonstrates the advantages of capacitance grading, where using materials with different permittivities improve stress distributions, lowers peak electric stress, and enhances the insulation efficiency and operating reliability of high voltage power cables. Okay, this slide presents the analytical comparison of capacitances in coaxial structure with two different dielectric layers. Um, this example is very similar to one of your question in your major two. So the inner electric is this assigned capacitance C1, while the outer dielectric is presented by C2. Using the standard capacitance formula for coaxial geometrics, which depends on the permittivity and the logarithmic ratio of um, R. So the ratio of C1 over C2 is can be derived. So this ratio clearly shows that capacitance is directly proportional to the relative permittivity epsilon R and inversely proportional to the logarithmic term of the R's, Bohr R's, inner R's and outer R's. So by substituting the given dielectric constants and geometric diameter dimensions into the expression, the final ratio is calculated as approximately 1.667. So this result also highlights how both material properties and physical dimensions influence the overall capacitance distribution in multi-layer dielectric systems, which is particularly important in the design of cables and high voltage insulations structures. Okay, this slide continues the analysis by relating the capacitance ratio to the voltage distribution across the two dielectric layers. So since the charge Q is the same in both regions, so the capacitance can be expressed as C1 is equal to Q over V1 and C2 is equal to Q over V2, leading to relationship C1 over C2 is equal to V2 over V1. So from this, we can find the V2 also, and considering the total applied voltage is 100 kilovolts, so we can find V1 and V2. The slide then proceeds to evaluate the maximum electric field in the inner electric dielectric. So using the expression E maximum 1 is equal to V1 divided by R1 ln R1 divided by R2, where the given dimensions are R1 is equal to 1 centimeter and R1 capital letter is equal to 2 centimeters. So, and finally, the general expression, the maximum for the maximum electric stress in a coaxial system is presented as G maximum is equal to 2V over D log D over T. Um, so as I told you, this one is very similar to one of your question for major two. So in overall, this slide highlights how the voltage is unevenly distributed across dielectric layers depending on their capacitances and how this directly affect the electric field stress within the insulation, which is critical for reliable HV cable design. Okay, this slide focuses on the calculation of electric field distribution within the inner electric layers and layer for of a coaxial system. So you just need to replace the values, and you can find the values again for um, um, outer diameter. Also, you can find you can use these equations. So in this slide compares the electric field distribution in a cable under two different insulation conditions: non-uniform or graded insulation and homogeneous insulations here. So for the given geometry, where the inner radius R2 is equal to 2 centimeter, and outer radius is 4 centimeters, and an applied voltage V2 is equal to 62.5 kilovolt. The maximum electric field occurs at the conductor surface and is can be calculated uh, by using of this equation, is equal to 45.1 kilovolt and kilovolt per centimeter, while the minimum field at the outer boundary is equal to 22.5. So this shows a relatively more balanced field distribution. However, when homogeneous insulation uh, is used with higher voltage of 100 kilovolt, the electric field becomes highly non-uniform, you can see, and reaching a much higher maximum value of 72.1 kilovolt per centimeter near the conductor, and dropping significantly to 18 kilovolt per centimeter at the outer surface. So this comparison highlights that homogeneous insulation leads to greater electric stress concentration at the inner conductor, which can increase the risk of insulation failure again. Therefore, proper insulation design such as grading is essential to achieve a more uniform electric field and improve cable reliability. Okay, this slide illustrates how the electric field varies with radius in a cable for two cases: homogeneous insulation and graded insulation. So in the case of homogeneous insulation, the electric field is highly non-uniform with a very high value near the inner conductor. You can see here, inner conductor is very high, so that rapidly decreases as the radius increases. So when radius increases, rapidly decreases. So this creates a strong electric stress concentrations at the inner surface, which is the most critical point for insulation failure. In contrast, the graded insulation curve shows the, more control and smoother variation of the electric field. By properly designing the insulation layers with different permeabilities, the electric stress is redistributed more evenly across the insulation thickness. So as a result, the maximum electric field is reduced and the difference between the inner and outer stress levels becomes smaller. So this demonstrates the key advantages of graded insulation. It minimizes peak stress and improves the overall reliability and lifespan of the cable system. Okay, the slide highlight the main practical limitation of using the graded insulation cables design. Although graded insulation is theoretically very effective in achieving a more uniform electric field distribution and reducing peak stress, its implementation is constrained by material availability. So the material should be available. So intersheath grading is a method of cable grading in which a homogeneous dielectric material is used throughout the insulation. So instead of varying the dielectric properties, the insulation is divided into multiple layers by inserting metallic intershields between the core and the outer lead sheets. So these intersheaths are maintained at suitable potentials, which helps in controlling and redistributing the electric field across the insulation. As a result, the electrostatic stress is made more uniform, reducing the maximum stress on the dielectric and improving the overall insulation performance of HV cables. This slide present the uses of an intersheath as a practical method to reduce electric stress in cable insulation. An intersheath is an additional conductive layer placed between the inner conductor and the outer sheets, and it is connected to an intermediate voltage through a tap transformer. By doing this, the total applied voltage is divided into smaller portions across different sections of the insulation. As illustrated in these figures, this leads to a more uniform voltage distribution and significantly lowers the maximum electric stress near the conductor, which is typically the most critical region. So consequently, the dielectric material experiences less electrical stress, improving its reliability and reducing the likelihood of insulation failure. So this technique is especially useful when ideal graded insulation cannot be achieved due to material limitations. So I want to stop my lecture here, and let me